Hello everyone and welcome to day 25 of the Jamb Physics in 40 Days series. This series is brought to you by Oyalen, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you should be able to gather all the necessary tools and skills that will help you ace your next Jamb Physics exams. So if you're preparing to have the Jamb exams and one of the subjects in your subject combination is physics, then this video is specifically made for you. So trust me, you do not want to miss any of the videos in this series. I've been able to go from day 1 up, this is day 25, and then it continues until day 40. So please check out each of the videos in the series. What we've been able to do in each of the videos is that we look at the individual topics that are in the Jamb Physics curriculum. We give you a crash course to it and tell you what is expected of you as a candidate writing the exams, and then we go on to solve past questions on those topics while giving you some tips that help you answer the questions with higher accuracy. So please check out each of these videos, and also don't forget to subscribe to the channel. It is very important to us that you are subscribed to the channel because that's your way of helping us to be able to make more helpful content like this. And we also expect that you please share the video, ensure that it reach as many that are really in need of content like this. So please continue to share the videos and also drop a like. And if you have any question at all that you'd like to ask us on what we are doing, or perhaps during your study time you come across a question that you would like help with, please drop them in the comment section and we'll definitely attend to every one of your comments. Now, day 25 is about refraction of light through plane and curved surfaces. Now, in the previous videos, that was for day 24, we looked at reflection of light through plane and curved surfaces. Now, some of the things we did there are also going to have similar effects when we are talking about refraction of light through plane and curved surfaces, but with a slight twist in this case. Now, when we say reflection, it means it is bouncing off from the surface. But refraction means that the light is going to go through the surface, but there's going to be a change in direction and speed of the light. When a light is moving from one medium to another, because of the difference in density of this medium, it causes the light rays to bend slightly. And as a result, there will be a change in speed, just as there is a change in wavelength. The only thing that remains constant is the frequency, because that is determined by the source of the wave. And the frequency of light wave will remain constant whether it's moving from one medium to another. It only depends on the type of light source, whether it is a radio wave source, whether it's a UV source, whether it's an infrared source, whether it's a visible light source. That is what determines the frequency of the light. But the wavelength and velocity can be changed based on the medium that light wave finds itself. So, as far as this topic goes, what JAMB expects of every candidate are listed here in the objectives. They expect that every candidate should be able to interpret the laws of refraction, and that there are two laws for refraction. The first one states that the incident ray, the normal and the refracted ray at the point of incidence all lie on the same plane. While the second statement for the law is according to the Snell's law. It's actually called the Snell's law, and it says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, and that constant is known as the refractive index. So it's often written like this. Let's say if light is moving from air to glass, for example, we'll then have sine angle of incidence over sine angle of refraction. This can also be written as small letter n. So in case you find it like that, they are still talking about the same thing. It is called the refractive index. So that's the interpretation to the laws of refraction. Now, secondly, they expect that every candidate should be able to determine the refractive index for glass, for liquids, using this Snell's law. So if you are given the information such as the angle of incidence, angle of refraction, you should be able to apply Snell's law. Now, this also works when you are given the velocities, because you can also do it as the ratio of the velocities in the two media to get your refractive index. It also applies to the wavelength as well, because the ratio of the wavelength will also give you the refractive index. Don't forget that the only thing that remains constant is frequency of the wave. So that one cannot work to get the refractive index since it remains constant. Now, another thing that is expected is that you should be able to determine the refractive index using the principle of real depth and apparent depth. Now, I'm sure you would have come across this kind of situation whereby you put an object into a bowl filled with water, for example, and then it appears as if the object is closer to you than it is actually. Because you are looking at it, it looks like it is close, but when you dip your hand to check it, you see that it's actually deeper than what you thought it was. Another thing like that is when you put a stick into a pool of water. It appears as if the stick is bent. Now, this is also one of the effects of refraction of light as it moves from air to water. So using that principle, you should also be able to find the refractive index, as the refractive index N is given as real depth over apparent depth. Now, this equation helps to solve for refractive index in the cases where you have the real depth and apparent depth. And in case you know the refractive index, you can also use it to find the real depth or the apparent depth. Now, some of those refractive index that we should know is that, for example, the refractive index of glass is approximately 1.5. That's refractive index from air to glass. Now, refractive index from air to water is 1.33 thereabout. It is approximately, not exactly that, meaning it can change depending on the nature of the glass you are working with or the type of water you are working with, whether it has impurities or not. These kind of things can affect the refractive index, but it's usually approximately these values that I have stated here. So when you're working with a question like this, do not assume it to be that. It will always be given, whether it is 1.5 or 1.33. But I'm just giving you this just in case, so that you can know when you see values like this that this is what the question really talks about. Now, another thing is that you should be able to state the conditions necessary for total internal reflection to occur. Now, total internal reflection occurs when a particular wave travels from a region where it is more dense to a region that is less dense, and that the angle of incidence is greater than the critical angle. Those are the two conditions that makes total internal reflection to occur. And that also can lead to the formation of what is known as a mirage, which is also one of the things that is expected of you in this topic. Now, another thing is that you should be able to examine the use of instruments such as the periscope, the prism, binoculars, and optical fibers, as they are used for refraction of light through plane and curved surfaces. And then you should be able to apply the principle of total internal reflections to the formation of mirage, which is what I've just mentioned earlier, that when light travels from a more dense to a less dense medium and it travels at an angle that is greater than critical angle, total internal reflection is going to occur, and it can lead to the formation of mirage, whereby you see something that looks like a body of water ahead of you, and then it is not really there. It is due to total internal reflection. And then you should also be able to use the lens formula and ray diagram to solve optical numerical problems. Just like we did in the case of reflection, we also do the same thing for refraction, especially through lenses. For reflection, we did it through mirrors, whether it's plane mirrors, whether it's curved mirrors. Now, in case of curved mirrors, I mentioned in the video for reflection that what we know as the concave mirrors that converges. In case of mirrors, when you come to lenses, that is done by the convex lens. The convex lens is what is the converging lens, while the concave lens becomes the diverging lens. And what you should know is that the mirror formula still holds, and the mirror formula states that 1 over f equals 1 over u plus 1 over v, where all of them hold their natural definition, where f is the focal length, u is the distance of the object from the mirror, v is the distance of the image from the mirror. And don't forget that v can be positive or negative depending whether it is a real image or a virtual image. So all the things we talked about when we're talking about the concave mirror, you can apply the same thing to a convex lens, where they form real images as long as you are from the focal length and beyond it. But the moment you go between the focal length and the pole of the lens, you then form virtual images. Whereas for the concave lens, you are always going to get virtual images. So that's how it works in the case of lenses. Now, another thing that is expected is that you should be able to determine the magnification of images, which retains the same equation where magnification m equals to image height over object height, which is the same thing as v over u. And then finally, you should be able to calculate the refractive index of glass prism using the minimum deviation formula. Now, this works in the case of triangular prism. So you should be able to know that the refractive index n can be given as sine of a plus d, this minimum deviation, over 2 all over sine, this should be sine, then a over 2. So this equation works when you are working with triangular prisms to find the refractive index. Now, for a deeper understanding of what I've just been mentioned now, you can check out our video where we actually discuss refraction of light in greater details. Now, in that video, you'll find where we solve different cases for whether it's a rectangular prism, triangular prism, or concave lens, or convex lens. We also talked about lens power, amongst other things that is expected of every student taking physics and is going through refraction of light. We did it in more detail, but for the purpose of the preparation for JAMB is why we are making this video. So we'll instead move to solving past questions that borders around this topic, and then we'll show you some tricks and some tips that will help you to solve with greater accuracy as we go. So if you're ready, get your materials and let's solve some problems. This question gives us that the velocity of light in air and glass are 3.0 times 10 to the power 8 meters per second and 2.0 times 10 to the power 8 meters per second respectively. So that is, this is the velocity in air while this is the velocity in glass. And then we are to find the sign of the angle of incidence if the angle of refraction is 30 degrees. Now, let's solve that. What we're going to use is refractive index n equals velocity in air over velocity in glass. And then we equate this to the other side of the equation where we have the same refractive index to be sine of angle of incidence over sine angle of refraction. So you see that the two equations that work for refractive index are what we are going to work with. So we work with these two sides here now. So velocity in air is given as 3 times 10 raised to the power 8. Now divide that by velocity in glass, which is 2 times 10 raised to the power 8. And then we equate this to sine angle of incidence over sine angle of refraction is given as 30 degrees. Now, when we work with this cancels out immediately. Now, we can cross this to the other side and then say sine angle of incidence, which is what we're asked to look for, would then be sine 30, which is 0.5 or 1 over 2. So we can write that 1 over 2 multiplied by 3 over 2. Now, this would give us 3 over 4, which is 0.75. So the correct option here is D. Which of the following conditions are necessary and sufficient for total internal reflection to take place at the boundary between two optical media? Now, I did mention this at the beginning of this video, that there are some conditions that must be met for total internal reflection to occur. And the first one is that the light must be traveling from an optically denser medium to a less dense medium. For example, hot air to cold air is one of those things that can lead to total internal reflection. So from optically more dense to optically less dense medium. And then secondly, the angle of incidence has to be greater than the critical angle. Those two conditions must definitely be met for total internal reflection to occur. So now let's look at the conditions given and then find the correct ones there. Now the first one says light is passing from an optically denser medium to optically less dense medium. That is correct. It's a condition that must be met. The second condition here says that light is passing from optically less dense medium to optically denser medium. This is wrong. It's the reverse of the first statement, so it's definitely wrong. Now the third one says angle of incidence is greater than a certain critical value. That's correct. And then the fourth one says angle of incidence is lesser than a certain critical value, which is wrong. So we only have 1 and 3 as the correct conditions that must be met before total internal reflection can occur. So these two are what leads to total internal reflection. And that makes the correct option for this question option D. The refractive index of a liquid is 1.5. If the velocity of light in vacuum is 3.0 times 10 raised to the power 8 meters per second, the velocity of light in the liquid is therefore, so let's find the velocity of light in that liquid. Now, we know refractive index equals velocity in, now remember, the light is traveling now from vacuum to the liquid. So, and in vacuum, that is in air, to liquid. So velocity in air, and then velocity in liquid. So if we work with this, we're going to work with the refractive index here, which is 1.5 equals velocity of light in vacuum, rather, that's given as 3.0 times 10 raised to the power 8 meters per second. Now divided by velocity of air in the liquid. So we can then walk around this and say V therefore becomes, that's 3.0 divided by 1.5. All of these times 10 raised to the power 8, and it's in meter per second. Now 3.0 divided by 1.5 will give us 2.0. So that will be times 10 raised to the power 8 meters per second. So the correct option here is B. A microscope is focused on a mark on a table. When the mark is covered by a plate of glass 2 meters thick, the microscope has to be raised 0.67 centimeters for the mark to be once more focused. Now we are asked to calculate the refractive index. Now in this case, we're going to be using real depth and apparent depth to determine the refractive index of the glass. So solution. Refractive index N equals real depth over apparent depth. Now, the real depth is, according to the question, 2.0 meters, while the apparent depth is 2 minus 0.67 centimeters. Remember, this is in meters, right? So you have to convert this into meters in order to solve this part of the problem. So if you do this, this can then be written as 200 centimeters minus 0.67 centimeters. So what this would give us is 199.33 centimeters. So now refractive index N therefore becomes Now let's just work in centimeters all the way. So 2 meters will then be written as 200. Now divided by 199.33. This is in centimeter just as this is in centimeter, so they cancel out. Now what we'll be left with is 1.52, and that will be the refractive index, which is option A. A microscope is focused on a mark on a table. When the mark is covered by a plate of glass 2 centimeters thick, the microscope has to be raised 0.67 centimeters for the mark to be once more focused. So now we have to calculate the refractive index, and we're going to be using the real depth and apparent depth to get refractive index for this question. So here's the solution. So when you apply refractive index equals real depth over apparent depth, we should get our answer. Now the real depth is 2 centimeters, while apparent depth is going to be 2 minus 0.67, and this would be in centimeters as well. So that is our refractive index, therefore becomes 2 centimeters divided by, now the difference here is 1.33 centimeters. So centimeter cancels centimeters. Now 2 divided by 1.33 will give us 1.5037 and on like that. So when we look at the options, the closest we have is 1.52. So we go with that, which is option A. This question says an object is placed directly below a glass block of thickness 3.0 centimeters. Now we have to calculate the lateral displacement of the object if the refractive index of the glass is 1.5. Now what lateral displacement means is the difference between the real depth and apparent depth as observed. Now to solve questions like this, you can always practice with the exam phone app, and the link to download the app is going to be added to the description box of this video. So please do not forget to click that link and download the app and infuse some fun into your study time. I promise you, you're going to enjoy studying better than you've ever done before. And also, if you have any question, don't forget that you can always put it in the comment section of this video, whether it's about what we are doing presently or if it's about something you found during study that you like help with to get better understanding. Please put them in the comment section and we'll definitely attend to all of your questions. And don't forget to like, share, and subscribe to the channel as well. Thank you very much. Now let's go on to solve this question. So the first thing we're going to do is to relate refractive index N with real depth and then divide that by the apparent depth. So let's put in the values now. The refractive index is given as 1.5, and this equals real depth, which is 3.0 centimeters divided by apparent depth. Now, what this implies is that the apparent depth equals 3.0 centimeters divided by 1.5. So now we can say the apparent depth equals, now when you divide this, that will give you 2.0 and it's in centimeters. Now remember, the question itself asks for lateral displacement, and I did mention that lateral displacement means the difference between real depth and apparent depth. So lateral displacement equals 3.0 centimeters minus 2.0 centimeters, and that gives us 1.0 centimeters, which is in option A. This question says light of frequency 6.0 times 10 raised to the power 14 hertz traveling in air is transmitted through glass of refractive index 1.5. Now, to calculate the frequency of the light in the glass. Now, many are always in a hurry to answer questions like this, and they immediately apply equation where you say refractive index equals, remember there's an equation that says n equals velocity in air over velocity in glass. So they believe this same thing. There's another one that says wavelength in air over wavelength in glass. So they believe there should be another one that says frequency in air over frequency in glass. And if you apply that, you will arrive at the answer 4.0 times 10 raised to the power 14 hertz. However, that is wrong. This question is meant to test your knowledge on the theory of waves. Now, when a wave, including light wave, travels from one medium to another of different densities, the velocity will change. Okay, velocity will change as well as the wavelength. Okay, so if the velocity like in this case, velocity of light wave in air is greater than the velocity in glass. So since velocity will reduce as it gets into the glass, the wavelength will also reduce as it gets into the glass. But one thing always remains constant, and that is frequency. So frequency remains constant. Now, the reason is because the frequency of a wave is determined by the source of the wave and not the medium. So whether it's in glass, whether it's in air, whether it's in vacuum, whether it's in water, the frequency remains the same. It is dependent on the source of the wave. So in this case, the frequency of this light wave will not change even as it moves from air into glass of refractive index 1.5. So our answer remains the same as the frequency before, which is 6.0 times 10 raised to the power 14, which is in option B. If the refractive index of a medium in air is 2.0, what is the critical angle for this medium? Now, when you ask to find critical angle, this is what we do. The sine of the critical angle equals 1 over the refractive index. So this means sine C equals 1 over refractive index is 2. So we can then say critical angle equals sine inverse of 1 over 2. Now sine, what gives us 1 over 2? That is sine 30. So therefore critical angle is 30 degrees. So the correct option here is A. A lens of focal length 12.0 centimeters forms an upright image 3 times the size of a real object. The distance between the object and the image is, now in this case, we're looking at a lens that has a focal length of 12 centimeters. So let's put that down. Focal length F is 12.0 centimeters, and the image is 3 times the size of the object, so magnification M equals 3. So since we don't have the object distance nor the image distance, we're going to apply M equals V over U, which implies that V equals M multiplied by U. So V equals M, which is 3, and then U is still U. So V equals 3 times of U. Now, let's apply the length formula. 1 over F equals 1 over U plus 1 over V. Now, this becomes 1 over F equals 1 over U plus 1 over 3U. Now, let's bring that here. This is 1 over 12 equals 1 over U plus 1 over 3U. From here, we can then go on to say 1 over 12 equals, LCM here is 3U. This will give you 3 plus 1. So 1 over 12 equals 4 over 3U, which implies that 3U equals 4 times 12. So 3U equals, now 4 times 12 is 48. And this implies that u equals 48 divided by 3, and this will give us 1 here in 18, 3 in 18, that's 6. So we have 16 centimeters for u. And then we can say v equals 3 times u, which is 16. And this would give us back to 3 times 6 is 8. So 48. V is 48. So working with this, we can then go on to find the distance between the object and the image. Now, since we get positive answers for u and v, that tells us it's a real image. So they are both going to be formed in front of, since it's a lens, of course, real image will be formed behind the lens. So the difference between this will give us the distance of the object from the image. So let's work with that. The distance between object and the image is then 48 centimeters minus 16 centimeters. 8 minus 6, that's 2. 4 minus 1, that's 3. So we have 32 centimeters, and that is option D. Calculate the angle of minimum deviation of a 60-degree prism of refractive index 1.5, given that sine inverse of 0.75 is 49 degrees. Now, if this were not given, we would have to actually find the sine inverse of that. And since we know that Jamb does not allow the use of scientific calculators, that is why you see that they would give you cases like this. They will give you hints of the sine inverse of some angles like that you will be needing in your calculation. So let's see how we work with questions like this. Now, refractive index for triangular prism, where we are using minimum angle of deviation and the likes, is given as sine of a plus d divided by 2 over sine a over 2. So let's work with this. So 1.5 equals sine 60 plus d divided by 2 all over sine 60 divided by 2, where a is 60. So we can easily work with this and then say 1.5 equals sine 60 plus d over 2 all over sine 30. So when we cross multiply here, remember that sine 30 is 0.5. So we're going to be having 0.5 multiplied by 1.5, and we equate that to sine of 60 plus deviation over 2. Now this would give us 0.75, and this equals sine 60 plus d all over 2. So we can then find the inverse sine of this to eliminate sine from this side. So we can then say 60 plus d divided by 2 equals the sine inverse of 0.75. And then when we cross multiply here, 60 plus d then becomes 2 multiplied by the sine inverse of 0.75 is given in the hint as 49 degrees. So from here we can then say d equals, now when we multiply this, what do we get? 2 times 9 is 18, so 8 carry 1. 2 times 4 is 8. 8 plus 1, we have 98 degrees. And then bring 60 to the other side, becomes minus 60 degrees. So the minimum deviation is then 98 minus 60, which will give you 38 degrees. So the correct answer is in option A. The distance between an object and its real image in a convex lens is 40 centimeters. If the magnification of the image is 3, calculate the focal length of the lens. So, to solve this, let's see what we have. The distance between object and real image is 40 centimeters. So, u plus v is 40 centimeters. Let's call this equation 1. Then we are told the magnification m equals 3. And what this implies, if we apply m equals u over v, we can then say 3 equals u over v. And this means that, sorry, this is v rather over u. Let me correct that. V over u. Okay, so what this means is that v is thrice of u, where v is image distance and u is object distance. So we can use this to get the value of v just as much as we can use it to get the value of u. So if we put v here, we'll say, if you substitute this, this is equation 2 now. If you substitute it into equation 1, we can then say u plus v, which is 3u, equals 40 centimeters. What this means is that 4u equals 40 centimeters and then u is 10 centimeters. So now that we have u, we can then solve this other part to get v. So v is 3 times of u, which is 10 centimeters. So that is v is 3 times 10, which is 30 centimeters. So the question itself says we should find focal length, so we apply length formula. 1 over f equals 1 over u plus 1 over v. So we can then say f equals uv over u plus v. Now uv, that is, u is 10, multiplied by v, which is 30, over u plus v, that gave us 40. So f equals 10 times 30 will give us 300. Now divide that by 40. You see 0 cancels 0. So what do we have left? 4 will go in 30 7 times. Because 4 times 7 is 28. So you remember 2. Now if you add the decimal point, that will give you a 0 to it. So 4 in 20, and that is 5. So we have 7.5 centimeters as the focal length. And that is what we see in option C. So we go with C. A lens of focal length 15 centimeters forms an erect image which is 3 times the size of the object. Now the distance between the object and the image is so from here we see that f, which is the focal length, is 15 centimeters, and we are told that the magnification is produced 3 times the size of the object. So if we say m equals v over u, and m is 3, that is 3 equals v over u, which implies that v equals 3u. Now we can use this to find u and then use it to find v, so that we can find the distance between the object and the image. So let's solve. 1 over f equals 1 over u plus 1 over v. This is the length formula. So 1 over 15 therefore becomes 1 over u plus 1 over. Now v is 3u. Now we can then say 1 over 15 equals, now when we take LCM here, that will be 3u. Now u here is 3. 3 times 1 we have 3, plus 3u here 1. 1 times 1, 1. So 1 over 15 equals 4 over 3u. So when we cross multiply, 3u equals 4 times 15. So we can say 3u equals 60, which implies that u is 60 divided by 3, that is 20 centimeters. And v, which is thrice of this, of course we solved it already, 3u, that is 60 centimeters. So now we have the value of v and u. Now this is a real image because both of them are positive. So in that sense, we can then find the distance between them by finding the difference. So the distance is then 60 centimeters minus 20 centimeters, and that would give us 40 centimeters. So the correct answer here is option D. Determine the focal length of a thin convergent lens if the power is 5.0 diopters. So to solve problems like this, at least the equation we use, the power of a lens is 1 over focal length. So we can then reverse this to find the focal length instead. So what this implies is that the focal length is 1 over power. But take note, whatever you solve here is going to be in meters. So since these options are already in meters, we're good to go. But in case you are to solve a question like this and the options are in centimeters, always remember to convert back to meters. And then if you are given focal length in centimeters and you're asked to find the power, you always have to convert that focal length to meters before you can find the power of the lens. So F here therefore becomes 1 over, the power is 5, so this would give us 0.2. Remember, this is in meters. So if our options were in centimeters, this would mean we have a 20 centimeter focal length lens. So in this case, our option is B. In this question, we are told that a light of wavelength 589 nanometers, nano here means times 10 raised to power negative 9, in a vacuum passes through a piece of fused quartz of index of refraction n equals 1.458. Now they are asked to find the frequency of the light in the fused quartz, given that the speed of light is 3 times 10 raised to power 8 meters per second. Now, oftentimes I see this kind of questions exactly like this send a lot of students into a wild goose chase. They begin to now compare first from refractive index, use that to find the wavelength of the light in the fused crystal, and then applying C equals F lambda to find the frequency. What you just have to always remember in cases like this is that the frequency of the light in air is the same as the frequency in any other material. The frequency remains constant. It does not change because it is determined by the source of the light and not the material of the medium through which it is transmitted. So whether it is in air, in vacuum, or in quartz crystals, or in water, frequency remains the same. So you don't have to use that ratio using the refractive index to go on that wild goose chase. You can just find the frequency in air or the frequency in vacuum, like in this case, and you will still get the same thing as what you would have gotten if you have first found the wavelength in the quartz crystals and then use that to find the frequency. So here's the best way to go. Remember that this is Jamb exam, so you have to do it the fastest way possible. So I just go straight and say my frequency equals speed of light over wavelength. And the speed of light is 3 times 10 raised to power 8, all divided by wavelength 589 times 10 raised to power minus 9. And from here, frequency is going to give you 5.09 times 10 raised to power 14, and it is measured in hertz. So the answer here is in option B. Now, do not forget that you can practice with many more questions like this when you use the Exam Fun app. The link to download the app is added to the description box of this video. Kindly click the link, download the app, register, and have fun while you learn. I promise you, it's an app that is created in such a way that your learning experience will be a whole lot more fun. And what's more interesting is that as you learn, you can also earn using the Exam Fun app. Now, please do not forget also to subscribe to the channel. Please take a moment to click the subscribe button if you have not done that yet. Please click the subscribe button and also hit the notification bell icon so that you get notified every time we put out a brand new content. And also don't forget to like the videos and also share it so that we can reach a wide range of audience who are in need of helpful content like this. Thank you very much for being a part of the series so far. I'll see you in the next video.